In the previous exercise, you solved this second-order linear homogeneous differential equation with these initial conditions. Recall that this differential equation describes a simple harmonic oscillator. This is a mass, which here has m equal to 1, which is attached to a spring with spring constant k equals 4. It describes the position, x of t, around the equilibrium position of the mass at x equals 0. In this case, because our equation didn't contain any damping, you found that the solution was a pure sine with amplitude at half and angular frequency 2. Recall that we saw an existence uniqueness theorem for initial value problems. This told us that if we had an nth order linear ordinary differential equation and n initial conditions, then we were guaranteed to find that a unique solution would always exist. In this case, we have a second-order differential equation, and so since we provided 2 initial conditions, we were guaranteed to have a unique solution. This type of problem is known as an initial value problem because we supply conditions at the beginning of our experiment, i.e. at time t equals 0. Initial value problems are often called IVPs for short. However, sometimes we are interested in slightly different scenarios. For example, consider the same spring mass system for which we have a mass positioned at x equals 0, at time t equals 0, but we're interested in finding the solution such that our mass passes through some point, say the point x equals 1, at some later time in the future. We will still have the same differential equation to describe this scenario, so that x double dot plus 4x equals 0. We'll have a condition so that x at 0 is equal to 0, but we now have a different condition that says that our position at some later time t equals t1 is equal to 1. So we now want to find the solution to this problem on a time interval where t goes between 0 and this later time t1. Because we're specifying the conditions at the ends of our time interval, this is known as a boundary value problem, or a BVP for short. The general solution for this problem will be exactly the same as for the initial value problem. That is, that the general solution, x of t, is equal to a cosine 2t plus b sine 2t, where a and b are 2 constants which will be determined by the boundary conditions. So let's now apply those boundary conditions. That is, let's substitute the value t equals 0 and t equals t1 into our general solution, and then equate the general solution to each of these boundary values. So the first condition will tell us that a times cosine of 0 plus b times sine of 0 has to equal 0. So that's our first boundary condition. And then the second boundary condition will tell us that a times cosine of 2t1 plus b times sine of 2t1 has to equal 1. Let's have a look at this first equation firstly. We know that sine of 0 is always equal to 0, so this term vanishes. And then this first equation just tells us that a times cosine of 0 is equal to 0. But cosine of 0 is 1, so this first equation just reduces to telling us that a has to equal 0. If a is equal to 0, then this first term vanishes from the second boundary condition, and we're just left with the condition that b times sine of 2t1 has to equal 1, which we can then rearrange to tell us that b has to equal 1 divided by sine of 2 times t1. So then we can just write down the solution to this boundary value problem, which is that x of t is equal to sine of 2t divided by sine of 2t1. Now that we have the solution, we could use this, for example, to find the initial velocity that we would need to supply to our mass in order that it passes through the point x equals 1 at some time t equals 1. But let's have a look at this solution in a little bit more detail. In particular, let's look at the denominator. Notice that if sine of 2t1 is equal to 0, then this expression doesn't make any sense. Remember that sine of 2t1 equals 0 has multiple different solutions. For example, t1 equals pi over 2, pi, 3 pi over 2, and so on. When t1 takes on one of these specific values that make sine of 2t1 equals 0, then our boundary value problem does not have a solution. This is in contrast to what we saw for initial value problems, where the existence in uniqueness theorem meant that we would always have a solution. This is something that is different about boundary value problems. In fact, for boundary value problems, there are 3 different possibilities. The first possibility is that we have a unique solution. This is the case for this boundary value problem, provided that t1 is such that sine of 2t1 is not equal to 0, so that this expression makes sense. In that case, we do indeed have a unique solution to the boundary value problem. The second possibility is that we have no solutions. This occurs for this boundary value problem whenever t1 takes on one of the values that makes sine of 2t1 equal to 0. So in that case, we have no solution whatsoever. The third possibility is that we have multiple solutions. This would violate the uniqueness part of the uniqueness theorem, and is a possibility for boundary value problems that you will see in later exercises. This was a somewhat artificial example of a boundary value problem, but we used it to compare with the initial value problem that you had solved before the video. Generally, boundary value problems arise when the independent variable is position rather than time. This is because it's more natural to want to specify conditions at different points in space rather than at different points in time. You will see more natural examples of boundary value problems in some of the problems and videos that follow this one.